Hello children, once again welcome to Physics with Sanoob Healing Medical Aspirations. In this video we will be discussing electric charges and fields. Okay, see all previous questions of NEET will be discussed in this video, and before that the questions asked for AIPMT also. 2-point charges A and B having charges plus Q and minus Q respectively are placed at a certain distance apart, and the force between them is F. If 25% charge of A is transferred to B, then the force between the charges becomes, see, from this Q by 4 plus Q by 4 is taken. So the charge here will become 3 by 4 Q. Okay, that plus Q by 4, when it is added with the minus Q, it will become minus 3Q by 4. So ultimately, the charge on the first particle will become plus 3Q by 4, and the charge on the second particle will become minus 3Q by 4. Or initially the charge on both the particles were Q each. Okay, and after this charge transfer, the charge on each particle will become 3/4 of the original charge. Okay, so F dash, F is proportional to Q square. Okay, finally the charge on each particle, that is Q dash, equal to 3 by 4 Q. As F is proportional to Q square, because see, force will be like this. F equals to this is K, the constant of proportionality, then Q1 Q2 each equal to Q, so it will be Q square, okay, divided by R square. K we are not changing, we cannot change. R also we are not changing, we are changing only this Q. Okay, so F dash divided by F, we can write Q dash by Q whole square. Okay, Q dash by Q is 3 by 4, so 3 by 4 whole square, or it is 9 by 16. So F dash will be 9F by 16. So this is the correct option. That is, two identical charged spheres suspended from a common point by two massless strings of length L. See, this is length L. See, this is length L, right? This is length L. Okay, and this separation is see, that is separation D. It is much smaller than L. Okay, or this L is much longer than this separation small d. What does it mean? This theta will be very small. Theta will be very small. Okay, now what are the forces acting on two identical charged spheres? Okay, see, the forces acting on the two spheres will be electric, weight will be acting like this, mg. Electric repulsion will be like this, okay, F. Okay, this is electric repulsion, this is mg, and tension will be like this, okay, tension. So suppose at each moment, if it is in equilibrium, if the resultant force acting on it is 0 at each moment, okay, then this will be the case. Okay, this is angle theta, and it is very small. As it is very small, theta will be nearly equal to tan theta, and theta will be nearly equal to sin theta when theta tends to 0. Okay, so we can write tan theta equal to sin theta approximately. Okay, from here tan theta will be, see, the electric repulsion divided by weights. If the separation between the two spheres is x, the electric repulsion will be kq square by x square. Divided by weight, that will give you the tan theta. Okay, divided by weight is mg. That is also equal to sin theta. Okay, see, from this triangle, what do you get? Sin theta. Sin theta is opposite side, this one, divided by this hypotenuse. Okay, now see, the total distance is x. Total distance is x. So this will be x by 2. Okay, and this will be L. So sin theta will be x by 2 divided by L. X by 2 divided by L. Okay, now this can be written as kq square by mgx square, and here it will be x by 2L. Okay, this k is constant, mg is constant, and 2L is constant. So we will get q square proportional to x cube. Okay, all other factors are constants. So q square proportional to x cube. Let me differentiate both sides. So 2q differentiating with respect to time. So 2q into dq by dt proportional to 3x square, that is the differential of x cube, into dx by dt. Okay, and from here we will get dx by dt, see dx by dt here, let us write, see dx, let me write dx divided by dt. Okay, this is proportional to dx by dt proportional to this 2 and 3 are constants, and dq by dt, see charge, charges begin to leak from both the spheres at a constant rate, means dq by dt is constant. Okay, see dq by dt is constant, 2 is constant, 3 is constant. Okay, so we can say dx by dt proportional to q by x square, because all other factors are constants. That I have written here, dx by dt proportional to q by x square. Okay, and see here we have q square proportional to x cube. So q proportional to x raised to 3 by 2. Q proportional to x raised to 3 by 2. So this q can be replaced by x raised to 3 by 2 by x square. What is this dx by dt? That is the rate at which this separation decreases. Okay, or the speed with which these two spheres approach. Okay, so that dx by dt proportional to x raised to minus 1 by 2. Okay, v proportional to x raised to minus 1 by 2. Okay. Now let's see the next question. Two pith balls carrying equal charges are suspended from a common point by strings of equal length. Okay. The equilibrium separation between them is r. Now the strings are rigidly clamped at half the height. Okay. Now see, suppose there is a bead here, bead. Okay, and that bead I have dropped like this. Okay, and clamped here. Okay, at half the height. Okay, now see, in this final situation, the separation between these two pith balls is represented as r dash. I don't want to confuse you with r and r dash. So let me represent this as x. Okay, x. Okay, instead of r dash, let me use this as x. Okay. Now see, in this case, what are the forces acting on the pith ball? See, electric repulsion will be acting like this, and weight mg will be acting like this, and tension like this. Okay, the body is in equilibrium, so we can draw like this. See, weight will be mg, okay, electric repulsion like this, and tension like this. This is angle theta. Okay, this is mg and this is the electric repulsion. Okay, now see, from here tan theta will be electric repulsion divided by weights. Okay, when the separation is r, electric repulsion will be k q square by r square divided by weight is mg. And see, from here this is theta, and tan theta will be r by 2 divided by y. Okay, so r by 2 divided by y. Okay, say from this force triangle, tan theta is opposite side electric repulsion by adjacent side weights. Okay, from here we are using the distances. Okay, the opposite side, this is r by 2, and adjacent side, that is y. So r by 2 divided by y. Okay, from here we will get k q square divided by k q square divided by mg r square. K q square by mg r square, that r square I have taken to the right. Already there is an r. When r square comes, it will be r cube divided by 2y, that is equal to k q square by mg. Okay, and in the second situation, see, second situation, the electric repulsion is k q square by x square, where x is the separation. Okay, k q square by x square divided by weight is mg. And see, from the distance triangle, see, this will be x by 2 and this will be y by 2. So tan theta will be x by 2 divided by y by 2. X by 2 divided by y by 2, it will be x by y. Okay. Now see, we have k q square by mg. See, k q square by mg, we have r cube divided by 2y. So let me replace this k q square by mg with the r cube by 2y. That I have written, r cube by 2y. Okay, see, one more factor I have to write here, that is x square. In the denominator, that also I have written. See, this k q square by mg is replaced by r cube by 2y. The r cube by 2y. Then x square I have put as it is. On the right side, there is x by y. Okay, now when this x square is, see, this y and y can be cancelled. So x cube will be r cube by 2. So x cube will be r cube by 2. And x will be r by 2 raised to 1 by 3, or cube root of 2. X equal to r by cube root of 2. So this x will be r by cube root of 2. Okay. Now let's see the next question. Yeah, a charge small q is placed at the center of the line joining two equal charges capital Q each. The system of the three charges will be in equilibrium if small q equal to. This is a beautiful question. Okay, we have two equal and similar charges at the two extremes. This is capital Q and this is also capital Q. Okay, now see, in case of two charges, 2 point charges, see, if the charges are similar, the null point means the point where the intensity of electric field is 0. The null point will be in between them. If there are two positive charges, then there will be a null point in between them. If there are negative charges, there will be a null point in between them. Means if the charges are similar, the null point will be in between them. If the charges are dissimilar, the null point can never be in between them. Means, suppose you have a positive charge here and a negative charge here. Okay, and we have, say, three regions. This is 1, this is 2, this is 3. As these charges are dissimilar, the null point can never be in between them. Means here there won't be null point in the region 2. Null point will be either in the region 1 or in the region 3. But if these charges are similar, means both positive or both negative, then the null point will be definitely in the region 2, means in between them. Okay, that is one point. And the second point, the null point will be always closer to the smaller. Null point will be always closer to the smaller. Okay, now see, consider here we have two charges, no? Okay, and each equal to plus q, right? Each equal to capital Q. We do not know actually it is plus capital Q or minus Q. We do not know the nature of these two. But one thing is sure, these two are similar charges and they are equal charges. Okay, so the null point will be in between them. And the null point must be closer to smaller. Here, both the charges are equal. So the null point must be equidistant from both. What does it mean? At the center of the line joining these two charges, the intensity of electric field will be 0. Means at this position, the field is 0 or it is the null points because these two charges are similar and equal. So at this position, intensity of electric field is 0. So whatever charge you keep here, the force on it will be 0. Irrespective of the magnitude or nature of this charge, the force on it will be 0 because it is kept at a point where the intensity of electric field is 0. So the force on it will be 0 into Q. 0 into Q. So the magnitude or nature of that small q is irrelevant. Okay, the force on this will be 0. Means this q will be always in equilibrium. Whatever be the magnitude of this q, whatever be the nature of this q, it will be in equilibrium. See, we have to get a condition that the system is in equilibrium. Means all the three charges must be in equilibrium. Okay, see, the equilibrium of this we have already established. It will be always in equilibrium. Now, consider this charge capital Q. What is the condition of that small capital Q? Say it is, see this capital Q is at a distance r by 2 from small q. Please listen. This capital Q is at a distance r by 2 from small q and at a distance r from a similar charge capital Q. Now what about this capital Q? This is at a distance r by 2 from a small q and at r from a similar charge capital Q. What does it mean? Both these charges are under similar conditions. At a distance r by 2 from small q and at a distance r from capital Q. Both these charges. Means if this is in equilibrium, this also will be in equilibrium because they are under similar conditions. Okay, this is always in equilibrium. If any one of these two also in equilibrium, then the whole system will be in equilibrium. Okay, so we have to find the condition for the equilibrium of any of these two charges. Then the whole system will be in equilibrium. Okay, equilibrium means the resultant force on it will be 0. Let's consider this one. Okay, the force on it will be K, this capital Q into small q divided by distance r by 2 whole square. The force on capital Q due to the small q. Now the force on this due to this charge capital Q, that is K q square by r square. Okay, the resultant force on this is the sum of these two. That must be 0. Okay, so we will get K q divided by r square, then 4 small q plus capital Q equal to 0. So small q equal to minus q by 4. Okay, then the whole system will be in equilibrium. Okay, so minus q by 4. This is the correct choice. Now from this question you can have one more question. What is the minimum magnitude of capital Q? What is the minimum magnitude of capital Q? See, charge cannot be the fraction of the charge on an electron or cannot be the fraction of charge on a proton. Charge can be integral multiples of the magnitude of charge on an electron. So this charge capital Q is to be divided by 4. Then capital Q must be divisible by 4. Okay, because it cannot be the fraction of the charge on an electron. So this capital Q can be 4e or it can be 8e or it can be 12e, where small e stands for the charge on an electron. Okay, so this capital Q cannot be any integer value. It should be multiples of 4e, where e is the charge or the magnitude of charge on an electron. Okay, so the least possible value of capital Q is plus or minus 4e, plus or minus 4 times the charge, magnitude of charge on an electron. Let's see the next question. Two positive ions each carrying a charge Q are separated by a distance d. F is the force of repulsion between the ions. The number of electrons missing from each ion will be. See, F equals Q square divided by 4 pi epsilon 0 d square. D is the separation between them. Then charge Q, that is equal to Ne, where E is the charge on an electron. Then that will be equal to 4 pi epsilon 0 F d square, and N will be equal to 4 pi epsilon 0 F d square whole divided by E, electronic charge. When that E is taken inside the square root, it will become E square. Okay, so 4 pi epsilon 0 F d square, 4 pi epsilon 0 F d square divided by E square. This is the correct choice. Simple. Now let's see the next question. See, point charges plus 4q, minus q and plus 4q are kept on the x-axis at x equal to 0, x equal to a and x equal to 2a. See, similar problem we have done just before. See, in that case we had a charge plus q, plus capital Q here, and an identical plus capital Q here, and we have kept a small q here, and when the system is in equilibrium, okay, this small q will be equal to minus q by 4. That we have got. Okay, this is an identical situation. Capital Q equal to 4q and small q was minus capital Q by 4. Here it is true. This divided by 4 will give you small q and the negative of that. So in this case the system will be in equilibrium. Okay, now here we have got two equal and similar charges. Equal and similar charges. Then the midpoint of the line joining these two charges will be a null point where the field intensity is 0. So whatever charge you keep here, it will be in equilibrium. Okay, so the equilibrium of this charge is established. Now these two charges at the two extremes are under identical conditions. If any one of these two charges is in equilibrium, the whole system will be in equilibrium. Let's find the resultant force on this. If the resultant force on this is 0, it is in equilibrium, then this also will be in equilibrium, then the whole system will be in equilibrium. Let us find the resultant force on this. What is the force on this 4q due to this minus q? That is k minus q 4q divided by separation square. And the force on this 4q due to this 4q, that is k 4q into 4q, that is 4q whole square divided by separation is 2a whole square. Okay, and here we will get minus 4k q square divided by a square, and here in the numerator there will be 4 square means 16, and in the denominator there will be 2 square, that is 4. So 16 by 4 will be 4k q square divided by a square. Okay, the sum of these two equal to 0 means the resultant force on this charge is 0. So the resultant force on this also will be 0. The force on this is already 0. So the whole system is in equilibrium. Okay, now none of the charges in equilibrium, all the charges are in okay, all the charges are in equilibrium. Now we have to identify whether the equilibrium is stable or unstable, because we have got two choices. All the charges are in unstable equilibrium, all the charges are in stable equilibrium. So our answer is either C or D. Okay, now what about the stability of the equilibrium? It is unstable or stable? See, in electrostatics there is a beautiful, wonderful law that is called Earnshaw's theorem. Earnshaw's theorem. See, Earnshaw's theorem. Okay, this is Earnshaw's theorem. What is that? The equilibrium of a system of charged particles under the Coulombian forces alone can never be stable. That is Earnshaw's theorem. See, here the system is in equilibrium under the electrostatic forces alone, under the Coulombian forces alone. Then no doubt that equilibrium can never be stable. Okay, so all the charges are in unstable equilibrium. Now let's see the next question. The electric dipole is placed in an angle at an angle of 30 degree with an electric field of intensity 2 into 10 raised to 5 Newton Coulomb raised minus 1. It experiences a torque equal to 4 Newton meter. Calculate the magnitude of the charge on the dipole if the dipole length is 2 centimeter. See, this is a common question, typical question. Many times we have seen this in past NEET question papers. So you should know this. Torque experienced by a dipole kept in an electric field, tau equals P cross E. So we can write tau equal to P sine theta. P is the dipole moment, and it can be written as the product of either charge and the separation between the two charges, or let us say the length of the dipole. Okay, so this is the expression for torque, and the charge will be tau divided by Le sine theta. Theta here it is given as 30 degree. Torque is 4 Newton meter, that I have written tau. Okay, and length is 2 centimeter, right? Yeah, 2 centimeter means 2 into 10 raised to minus 2 meter. And see, intensity of electric field is given as 2 into 10 raised to 5, and theta 30, so sine 30 will be half. Okay, now see, this 2 and this 2 can be cancelled. Okay, 10 raised to 5 and 10 raised to minus 2 will be 10 raised to 3. When it is taken to the numerator, it will be 10 raised to minus 3, and 5 by 2 will be 2.5, not 5 by 2, it is 4 by 2. So it will be 2 millicoulomb. Okay, 2 millicoulomb. So it is 2 millicoulombs. That is a spherical conductor of radius 10 centimeter has a charge of 3.2 into 10 raised minus 7 coulombs distributed uniformly Okay, it's a spherical conductor. It's a spherical conductor. In case of a conductor, charge resides only on its surface. Okay. So what is the magnitude of electric field at a point? 15 centimeter. See, the radius is 10 centimeter. We have to find the electric field intensity at a distance 15 centimeter from the center. Okay, means it is outside the sphere. It is outside the sphere. Inside the sphere, intensity of electric field is 0 if it is a conductor. And outside the sphere, we have, see, this is the function of the intensity of electric field. Okay, it is equal to 0 as long as this R. R means it is the distance of the point of observation from the center. It is less than the radius of the sphere means the point of observation is inside. Field is 0. And this is the expression for the intensity of electric field outside. Okay, here small r equal to 15 centimeter. That is more than the radius 10 centimeter. So we have to use this formula that K equals 9 into 10 raised to 9 and charge it is given as 3.2 into 10 raised minus 7 coulombs. And this distance that is 15 centimeters, so 15 into 10 raised to minus 2 whole square. Okay, that see this we can write, see we have 10 raised to minus 2 whole square, that is 10 raised to minus 4. 10 raised to minus 4 and 10 raised to minus 7. In the numerator there will be 10 raised to minus 3 remaining. Okay, 10 raised to minus 4 here, 10 raised to minus 7 here. Okay, then we will get 10 raised to minus 3 in the numerator. 10 raised to minus 3 and 10 raised to 9 will give you 10 raised to 6. Let it be there, 10 raised to 6. Okay, 10 raised to 6. And here we will have 15 square. 15 square is 225. And in the numerator we have 10 raised to 6. 225, see, it is like 9, see 9, okay, this one, into 3.2 into 10 raised to 6 we got. And in the denominator there is 15 square, that is 225. Let me write it as 2.25 into 10 raised to 2. Okay, 2.25 into 10 raised to 2. Now this 10 raised to 6 by 10 raised to 2 will be 10 raised to 4. 10 raised to 4. Let it be there. Okay. And this 2.25 we can write 9 by 4. 9 by 4. This 9 and 9 will get cancelled and 4 will go to the numerator. Okay. And 4 into 3.8 will be, 4 into 3.2 will be 12.8. So 12.8 into 10 raised to 4. Or we can write 1.28 into 10 raised to 5 Newton Coulomb raised to minus 1. 1.25 into 10 raised to 5 Newton Coulomb raised minus 1. Okay, see, I am doing the calculations also. I am not leaving the calculations for you. See, you should practice these calculations also, then only you will be able to solve until you get the final answer. Okay, now let's see the next question. See, the electric field at a distance 3r by 2 from the center of a charged conducting spherical shell of radius r. See, radius is r and we have to find the intensity. See, the intensity of electric field is capital E at a distance 3r by 2 from the center. Means it is outside the sphere. The point of observation is outside the sphere. Outside the sphere, at a distance 3r by 2 from the center of the sphere, the intensity of electric field is E. Okay, the electric field at a distance r by 2, that is inside the shell. Okay, see, this is the shell. Okay, this is radius capital R. Okay, now r by 2 means it will be here, that is inside. And see, 3r by 2 will be like this. This is 3r by 2 at a distance 3r by 2 from the center. Here the intensity of electric field is capital E. But this point at a distance r by 2 from the center means the point of observation is inside the shell, where the electric field intensity will be 0. Okay, now so the field is 0. Okay. Now children, let's try the next question. A thin conducting ring of radius capital R is given a charge plus Q. Okay, given a charge plus Q. The electric field at the center of the ring due to the charge on the part AKB. Okay, due to the charge on the part AKB means, see, this is, see, field due to this part, okay, AKB of the ring is capital E, capital E. See, the field due to this part at the center of the ring is represented like this, intensity of electric fields. Okay. Now, the electric field at the center due to the charge on the part ACDB. ACDB means that is the remaining part of the ring. See, the intensity of electric field at the center of the ring due to the whole, due to the complete ring will be 0. Okay, so the resultant intensity of electric field at the center due to the complete ring will be 0. Okay, so the field due to this part AKB and the field due to the remaining part ACDB will be equal in magnitude and opposite in direction. Then only we will get the resultant field 0. Okay, so if the field due to AKB is along this line, then the field due to the remaining part will be just opposite to it, means like this. Okay, because the resultant field at the center due to the complete ring should be 0. Okay, so, or let us say the field, electric field due to the part AKB and the field due to the remaining part is field due to ACDB. Okay, this is the field due to the complete ring at its center. This must be equal to 0. Okay, so the intensity of electric field due to ACDB should be equal and opposite to the field due to AKB. Okay, field due to AKB is along KO, then the field due to the remaining part must be along OK, just opposite. So, intensity of electric field E along OK. See, a hollow insulated conducting sphere is given a positive charge of 10 microcoulomb. What will be the electric field at the center of the sphere? See, inside a spherical shell, the intensity of electric field is 0. Okay, everywhere inside. Okay, so the answer must be, what will be the electric field at the center of the sphere if its radius is 2 meters? Okay, it is independent of the radius, at the center it will be 0. Now, a point Q lies on the perpendicular bisector of an electric dipole of dipole moment P. If the distance of Q from the dipole is R, then the electric field at capital Q is proportional to, that is Kp by Rq. So it is proportional to P raised to 1 and R raised to minus 3. Okay, so P raised to 1 and R raised to minus 3. See, some questions are slightly difficult, you may feel, but majority of the questions are very simple. Okay, this type of questions you can expect. See, next again we have another simple question. Intensity of an electric field capital E depends on distance R due to a dipole is related as. See, here the position of the point, whether it is on the axis or it is on the perpendicular bisector or anywhere else, that is not mentioned. But in general, I have taken an arbitrary point. Okay, so anywhere the intensity of electric field due to a dipole is proportional to 1 by R cube. So E proportional to 1 by R cube. Now, an electric dipole consisting of two opposite charges of 2 into 10 raised to minus 6 coulomb each, separated by a distance of 3 centimeters, is placed perpendicular to an electric field of 2 into 10 raised to 5 Newton per coulomb. The torque acting on it is torque equal to P cross E. So it is P sine theta. Here the angle theta is between dipole moment and the field intensity, that is 90 degree. So we have, this is dipole moment Q into separation of the charges 2A, and it is given as 3 centimeter. Okay, charge 2 into 10 raised to minus 6. 2A is 3 centimeter. We have to convert it into meter by multiplying 10 raised to minus 2. Intensity of electric field is given as 2 into 10 raised to 5. Okay, and theta is 90 degree. So sine 90. Okay, so here we have 2 into 3, 6 into 2, that is 12. that I have written here, 10 raised to minus 6 and 10 raised minus 2, that is 10 raised to minus 8 into 10 raised to 5, that is 10 raised minus 3. So 12 into 10 raised to minus 3 Newton meter. Okay, so this is the correct option. Okay, now let us see the next question. See, there is an electric field capital E in the x direction. If the work done on moving a charge of 0.2 coulomb through a distance of 2 meter along a line making 60 degree with x-axis is 4 joule, then what is the value of capital E? See, this is the direction along which the body experiences a force, and this is the direction of the displacement at 60 degree with force. So work done will be F dot S. F is equal to QE. Then S, angle between them is 60 degrees, so QES cos 60. So intensity of electric field work done divided by QS cos 60. W, work done is 4 joule. Charge is 0.2 coulombs. 0.2 coulombs, and displacement S is 2 meter. Cos 60 is half. So 4 by 0.2 or 40 by 2, that is equal to 20 Newton coulomb raised to minus 1. So this will be 20 Newton per coulomb. Okay, now we have another, see, E dot ds equal to 0 over a surface, then the number of flux lines entering the surface must be equal to the number of flux lines leaving it. Okay, that is true. The magnitude of electric field on the surface is constant. The magnitude of electric field on the surface is constant, that need not be. Okay, all the charges must necessarily be inside the surface. Okay, the electric field inside the surface is necessarily uniform. Only the first statement. Okay, the total electric flux is 0. Means outgoing flux is taken as positive and incoming flux as negative. So here the total electric flux is 0. Okay, a sphere encloses an electric dipole with the charges plus or minus 3 into 10 raised minus 6 coulomb. Means dipole means there will be two equal and opposite charges. What is the total electric flux across the sphere? Total charge enclosed is 0, so the total electric flux through the surface will be 0. Now children, let's see the next question. What is the flux through a cube of side A if a point charge of Q is kept is at one of the corners? Suppose we have 8 identical cubes. 4 cubes are arranged like this on a tabletop, okay, and a charge small q is kept at the center like this. Another 4 identical cubes are kept or arranged over these 4 cubes, so that the combination of these 8 cubes is a big cube of edge equal to twice the edge of the smaller cubes, and the charge is at the center of this big cube. The total flux coming out of this charge is q by epsilon 0. It will be distributed symmetrically among the 8 cubes, so that the flux through each cube will be q by 8 epsilon 0. Okay, now let's see the next question. A charge capital Q is enclosed by a Gaussian spherical surface of radius r. If the radius is doubled, then the electric flux will remain the same. See, electric flux means the electric lines of force. See, this is a sphere, blue. Okay, this is a sphere of longer radius. Okay, this is at another sphere of still longer radius. See, whatever there is a charge at the center. See, whatever lines are passing through this sphere will be passing through this sphere and passing through this sphere, passing through any sphere surrounding that charge. So the electric flux means the total electric lines of force passing through any sphere enclosing that charge will be the same, irrespective of its radius. Okay, yeah, we have a wonderful question here. A hollow cylinder has a charge q coulomb within it. So the total electric flux through all the surfaces of the cylinder is q by epsilon 0. Total flux. Okay. And see, the flux through these n phases will be symmetrical. Flux through n phases will be symmetrical. If phi is the flux through this n phase, then the flux through this n phase also will be phi. Okay. Now let's see, if phi is the electric flux in units of volt second associated with a curved surface, phi is the flux through curved surface. Total flux is q by epsilon 0. Flux through the curved surface is phi. So the flux through the n phases will be Q by epsilon 0 minus phi. This is the flux through n phases. Q by epsilon 0 minus phi, of which half of it will be through this left n phase and the remaining half will be through the right n phase. Okay, here we have, this is the flux through the curved surface. Flux through the plane surface, let it be phi with the suffix p. We have two plane surfaces, here and here. So the flux through each plane surface is phi with the suffix p. So flux through two plane surfaces will be 2 into phi with the suffix p, and this is the flux through curved surface. If we find the sum of these two, we will get the total flux, and it is equal to Q by epsilon 0. Right? Now what we have to find out? We have to find out the flux through the plane surface, one plane surface. So it will be half of Q by epsilon 0 minus phi. See, the flux linked with the plane surface A, okay, only this one. That will be half of Q by epsilon 0 minus phi, this one. Now let's see the next question. See, the charge Q is located at the center of a cube. See, the total flux coming out of the charge will be Q by epsilon 0. As this charge is kept at the center of the cube, this whole flux Q by epsilon 0 will be distributed symmetrically among all the 6 phases. So the flux through each phase will be 1/6 of the total flux. That is Q by 6 epsilon 0. Q by 6 epsilon 0 is this one. Okay.